So if this set here is a basis for all the possible states a single particle can be in, then by definition the state of a single particle, a general one, can be written as an arbitrary linear superposition of those states. Now if we have n of those particles, we have to take the tensor product of the spaces, and that means that the complete basis is the arbitrary tensor product of all possible combinations of those basis states, and we need to have a complex number for each one of those. But because these coefficients are symmetric or antisymmetric with respect to particle exchange, depending on whether they're bosons or fermions respectively, there's a lot of redundancy in this description. And so we usually write it in terms of the occupation number notation, which looks like this. Which looks deceptively similar to the previous notation, but they're very different. In the previous notation, the nth slot describes the state of the nth particle, whereas things are quite different in the occupation number notation. For example, this second slot describes the number of particles in the second single particle state. As a sidebar, I'd like to note that this notation has introduced the idea that it's possible to have states with different numbers of atoms. For example, does that seem like a reasonable state? It has a superposition of two particles, one in each possible single particle state, and a state with one particle in it. In actual fact, when you start interacting systems with other systems and you have the possibility of particle exchange, you can indeed, for your subsystem, go into superpositions like that. So it can be a very useful state to include in your notation. How do we describe that in original notation? Well, if we have the Hilbert space for n particles, then of course we can't deal with it with that, so we have to have the tensor product of the Hilbert space for n particles for all the different n's, including actually 0. So the full space, and this is called the Fock space for particles, has the tensor product of the Hilbert space for all the different possible numbers of particles. So our original notation up here, which some people call first quantized notation, for historical reasons that we will attempt to forget, is actually just a subset of the full Fock space where we have a specific number of particles. Whereas our occupation number notation, which is sometimes called second quantized notation, for reasons that we will actively resist, is a subspace of our Fock space where we only allow symmetric or antisymmetric coefficients as appropriate. Now if we want to use this occupation number notation because it's got the built-in symmetries, then that's good, but we're not going to enjoy going forwards and backwards between the two kinds of notation, so we're going to want to do everything in the one notation. And that means we're going to need to deal with operators in occupation number notation. To that end, we're going to introduce the creation and annihilation operators. And they do exactly what their names imply. They create and annihilate particles. So the operator bj annihilates a particle from state j, and operator bj dagger creates a particle in state j. Now they're actually fully defined by their commutation relations, where we're taking the minus sign, in other words the normal commutator for bosons, or the plus sign, which is the normal anti-commutator for fermions. Normally people use no sign at all, just square brackets to mean the commutation relations and curly brackets to be the anti-commutation relations, but this is a more compact form. Now if we just switch over to bosons specifically for a moment, we can see what these operators do to boson modes, which is to say it simply annihilates one particle out of the jth mode or creates a particle in the jth mode with these coefficients out the front. And you can get those coefficients right by considering what happens to the vacuum. So if you annihilate a particle out of the vacuum, you should get nothing, and if you create a particle out of the vacuum, you should get something. So a completely arbitrary operator on our Hilbert space can be written in terms of creation and annihilation operators. That's fairly easy to see. Our general basis states just look like, in occupation number notation, a string of integers, and if I want to change those integers, so if I want to change that to some other string of integers, then it's pretty obvious that I can do that by applying a bunch of annihilation and creation operators. If m1 is bigger than n1, then all I have to do is do some creation operators, where I've got some bunch of coefficients from these factors that come out there, and then if I want to change the n2 to an m2, I can do whatever I need to do, either create or annihilate. I can change that number and so on and so forth. So if I just have a string of creation annihilation operators behind this state here, I can turn it into any other basis state I like. And if I can change any basis state into any other basis state, then some superposition of those will turn any state into any other state, and so I've got a completely arbitrary operator. You note that if I create a particle after destroying a particle, then I don't change the number of particles. But if I apply these two operators to that state, I actually get an eigenvalue out, which is just the number of particles. So in other words, this operator here has as eigenvalues the number of particles in state J. And so that is often called the number operator. And if all of this is sounding kind of familiar, that's not surprising, because this is all the same machinery we introduced when we were talking about harmonic oscillators all those years ago. And in fact, why is this coming up again? It's coming up again because the Hilbert space has exactly the same structure. It looks exactly like the tensor product of a large number of harmonic oscillators. And this actually explains the fact that bosons have exactly the same structure as the large number of harmonic oscillators goes a long way to explaining exactly why physicists are so fascinated by that system. It just seems to keep coming up again and again and again. So all that machinery that we used to use for harmonic oscillators, we can now use for any collection of fundamental bosons.